Extreme value theorem is going to deal with maximum and minimum points. Okay? Specifically, we are going to be looking at absolute maximum and minimum points. Before we really get into that, we need to like a quick review on what an absolute maximum would be, what a relative maximum would be, and same for minimums. So this first part is really like a review of pre-cal sort of stuff, because we talked about absolute and relative maximums and minimums in pre-cal. You even do it a little bit in Math 3. So that should hopefully be a pretty quick thing that we can get through, and then we're going to look at what this looks like for calculus. What are we going to have to do if we're finding these using calculus? Because they're going to give you a lot of these problems that are not on calculator active, right? If it's calculator active, we just type that into Desmos. We look for that like high point, right? But a lot of these are not going to be on calculator active. So finding the answers without a calculator is not something you know how to do yet. So an absolute maximum or minimum is the highest or lowest point on the entire function for the given domain. So if f of c is the absolute minimum of f on the interval I, then blank for all x in I. Okay? Here, don't worry too much about that I stuff right there. That is just the interval that you're looking at. So it might be from like 1 to 4, or it might be from -8 to 10, whatever interval you have. So for an absolute minimum, then f of c, which is going to be the y coordinate of your point, right? Because we could think like the point that goes with this would be c f of c. So your y coordinate at this point c is going to be less than or equal to f of x for any other x in the interval, right? So it has to be the lowest point. Now you can have more than one absolute minimum, but that would mean they all have like the same y value. For example, if you had a graph that looked like this right here, it would have absolute minimums at both of these points right here, but they would have the same y value. You can't have more than one y value, but it can happen at more than one point. Another example would be like a trig function, right? A sine function has an unlimited number of minimum points, but -1 is the minimum value of that function. So we're talking about the y values there. If you have a absolute maximum, then it's going to be similar, but f of c is going to be greater than or equal to f of x. Your y coordinate there is higher than the whole function anywhere else. Okay, absolute maximums and minimums are also sometimes called global maximums or minimums. Isn't that last point? Maybe extrema. I think that's what I meant there. Because sometimes they'll use the word extrema to mean the highest or lowest, right? So it's the extreme value. It's the name of the theorem that we'll be working with today, the extreme value theorem. Right, so extrema is one word we can use to mean maximums or minimums without them having to specify maximums or minimums. Okay, so relative max or min. A relative max or min is higher than the points around it. That's a very informal definition. It also can be known as a point where the graph switches from increasing to decreasing, or vice versa. Right? That's a more formal definition. Right? So whenever we talk about this, we're thinking about something like this graph right here. This point right here would be a relative maximum. It's not the absolute maximum. It's not the highest point on the whole graph, but it is higher than the points around it. And you'll notice here we switch from increasing to decreasing at that point. The formal definition for a relative maximum or minimum is that if there is any open interval containing C on which f of C is a maximum or minimum, then f of C is called a relative maximum or minimum. Now, open interval means parentheses or less than signs, not or equal to or brackets. So I've got, hopefully this will take me to where it's supposed to. Alright, so like if I have, for example, this interval, or this equation right here, we're pretty good at like seeing relative maximums, minimums, I think. I see that I have those there. The official definition here is if you can cut this graph off to a section where it would be the highest point, right? So, for example, if I'm thinking about that maximum, actually I'm going to copy and paste this. If I only look from maybe like negative 3 less than x less than 0, right here, let me pick a different color so that shows up. Like if I only look at this section of the graph, is there an absolute maximum on just that part of the graph? There is. If that blue piece was all that we had, this would be an absolute maximum. So if you can cut it off so that it would be an absolute maximum or minimum, if you just like cut off part of the graph, then that makes it a relative. Now, technically, absolute maximums are also relative maximums, right? So if I have something like, let's do a new one. Oh, gracious. Just want a new graph. Let's just hit the Desmos right here. If I just have like f of x equals x minus 1 squared minus 6, something like this. This point right here is an absolute minimum. You could still call it a relative minimum as well. The most specific name for it is an absolute maximum. But it is also, all absolutes are also, well actually, sort of all absolutes are also relative. What if I took this and from 0 less than or equal to x less than or equal to 7? What if I cut this graph off right here? Okay. Now, I still have an absolute minimum, right? That's my absolute minimum. Do I have an absolute maximum on the domain that I'm given? Do I have a highest point on this graph? I would, because my domain has been restricted. That highest point is at 30, right? My absolute maximum is 30. Is that a relative maximum? It's not switching from, like, increasing to decreasing. There's not an open interval. Now, this is also a little different than the way they do the definition in pre-calc. Probably forgot that anyway. So they would count relative maximums and minimums at the endpoints, which I don't really understand. This is not a relative maximum, but it is absolute. But that's only going to happen if you're on a restricted domain for that. All right, so let's go back over here because I feel like I've probably been making that more complicated than it really needs to be, right? So you guys have here 3 examples, and I want you to find all maximum and minimums for these. Now, let's just do one together because I want you to say it a specific way. So this one, do we have any maximums for this graph? We do not, because you cannot say infinity. So infinity would be like saying the speed limit is infinity, which means there just is no speed limit, right? So we wouldn't want to say the maximum is infinity, because that's like just saying there is none because it goes on forever. So we wouldn't say infinity, we would just say there are no maximums for this. But there is a minimum. What type of minimum could I call that? Absolute. Technically also a relative, but let's go most specific, absolute, right? So the way that I want us to write this is the absolute minimum is, you want to give the y value. What's the lowest y value you've got? -4. And then I would say which occurs at x equals, x coordinate is 3, right here. It is a really good practice for us to give maximum or minimums in this way, because sometimes they say find the maximum or minimum like it does here. That's the y coordinate. Okay? Sometimes they ask you find all x coordinates where the maximums or minimums occur, in which case you need the x part. Technically, to answer this question, you only have to have the first part. The absolute minimum is -4. That's all you have to have. But they interchange like how they ask the question so often for this that the safest way to answer these questions is the absolute minimum is y coordinate, which occurs at x equals x coordinate. Right? That way, if you misread what they were looking for, you still get the question right. Either way there. So do the other two there and try to use that formula sort of for answering those. It's more often they just ask you for the x coordinates of relative minimums, but if they did want the y coordinates, relative maximum is, I think it's 35 here, which occurs at x equals -3. And your relative minimum would be right here. It is 3, which occurs at x equals 1. Okay, there are no absolutes on that because you got arrows on the end of your graph. Now, 3 is a little bit more of what we're going to look at today, because for extreme value theorem, we'll be looking on closed intervals. So if I've got this graph right here, then I want to know highest and lowest point, and any points in between where I switch from increasing to decreasing or decreasing to increasing. But I don't really have that happen, right? So the very highest point on this graph is 12, is your y-coordinate, which occurs at x equals 7. So that absolute maximum is 12, which occurs at x equals 7. And then the absolute minimum, the very lowest point on this graph, is -4, which occurs at x equals 3. Okay, there. This point right here is just not really anything, right? If you go with the very general definition of a point that's higher than the ones around it, you might feel led to call that a relative maximum. But using the official definitions, it's not, because we don't switch from increasing to decreasing or decreasing to increasing there, or we can't put it on an open interval. We would have to include the endpoints for it to be the highest point. So we would just not call this anything right here. Okay, now extreme value theorem we're going to look at today is going to look most like example 3. So we have the extreme value theorem stated for us, and it's really a very simple idea. Extreme value theorem tells us if f is continuous on a closed interval from A to B, then f has both a minimum and a maximum on that interval. Okay, this is true for all different kinds of functions. Oh, excuse me. First of all, we can only talk about functions that are continuous on that interval, because now you could have some crazy things occur if you have jumps and stuff in the graph, right? But it's possible, like, you don't, like, if you have a jump, you could have, like, a line going off here, a line going off here, and you don't have a maximum or minimum. Well, those are weird. Yeah, because it have to be on a restricted interval. I guess you could have asymptotes. If you had asymptotes, you wouldn't have maximum or minimum, because this line goes on up forever, but it could still be on the closed interval that you're looking at. So it must be continuous, but as long as you're looking at a continuous function, there has to be a maximum or a minimum. So, like, just to think of a couple pictures of what this might look like. Let's say that we've got this crazy graph here. If it is on a closed interval, it has got to have a lowest point, absolute minimum. It has got to have a highest point, absolute maximum. Now let's think of some that might seem like they would be trouble. What about if I just had like a straight line like this? Does it have, if it's on a restricted domain, now if it has arrows on the end, extreme value theorem does not apply, right? But if it's on a restricted domain from A to B, do we have a highest point? Yes, it's right here. There's our absolute maximum. And do we have a lowest point on this graph? Right here, here's our absolute minimum. It's kind of like a boring one, right? But you still have a highest and a lowest. Can anybody think of one that they feel like's wrong? Like it doesn't have maximum or minimum? This one right here. Now, I don't like it. I really hate this idea here. I so hate this. But what is your absolute maximum if you have this line? Or where is your absolute maximum? Everywhere. Every single point is the absolute maximum. Because every point, like this, let's say this is 3 right here. The highest this graph ever goes is 3. All right, what is the absolute minimum of that graph? Every single point. 3 is the absolute minimum. So it is the maximum and the minimum at the same time, because it's just the same always, which feels wrong, but it's true, right? So like this would be a weird scenario, but every point is an absolute max and absolute min. Okay, that's a good one to think about for that would be like a sine function, right? So let's say that we had a sine function. Like here's 1, here's -1. let's say we were looking at it, sine, it goes through here. So if you had like a sine function that was restricted to just 2 periods of the graph, right? Sine, or it could be more, right? But this function, it has 2 places. Both of those are going to be absolute maximums, but it only has one absolute maximum. The absolute maximum is y coordinate. What's the y coordinate if this is y equals sine x? What's the highest that goes? 1. So absolute maximum is 1. So there's only one maximum, but when we say which occurs at, we got 2 places it happens. X equals, oh gosh, pi over 2, and x equals negative 3 pi over 2. Right, and then we could do the same thing for the minimums. There are two points that are absolute minimums, but there's only one y value that is the absolute minimum. Does that make sense? So like if we wanted to do minimums for this, we could say the absolute minimum is negative 1, which good gracious, what have I even done there? Which, come on, occurs at. That one's going to be x equals negative pi over 2, and x equals positive 3 pi over 2. Most functions are going to look like something like this or this, where you've got one absolute maximum, one absolute minimum. But it is possible to have more than one point where you get that absolute maximum or that absolute minimum. Or in the case of a horizontal line, and this would be the only case where this happens, every point is absolute maximum and every point is absolute minimum.
So the side function, wouldn't they also be relative?
They would. They're also relative. You would want to go with like the most. So if something is relative, but also absolute, you would generally want to go with absolute on that. And most of the time, they will not ask you a question where it says find all absolute and relative, like at the same time. Usually if they want absolute, they'll specifically say find absolute. You don't have to tell anything about relative for that. All right, and today we'll be looking at absolute because the absolute value theorem only applies on closed intervals, and it's only going to guarantee those absolute maximum minimums. So in order to know how to do this with calculus, we need to know about critical numbers. Okay? Critical numbers are points where the derivative of the function is equal to 0 or is undefined. Okay? So if I look at this graph right here, what are the x coordinates where I would have a 0 slope? Like my slope of if I drew in my tangent line, it would be a horizontal line. Yep, I would say it's 0, like right here. If I drew in that tangent line, horizontal slope. Okay, also at negative 3, and also right here at 2. What do you notice about those points on your graph? They are maximum minimum points, right? At least relative, possibly absolute, like in the case of the one at x equals negative 3. So, if you have a maximum or minimum, it's going to need to be at critical points. Now, undefined slopes are a lot harder to see. I don't intend for there to be one here. Actually, I can't remember what I did with this graph. It looks like it got a little bit of a sharp turn there. I don't know what I was doing. but they're a little bit harder to see. Usually, if there is a vertical tangent, they will say the graph has a vertical tangent at x equals 3 if they're asking you to do that from a graph for that. Or if you're doing it from an equation, we'll look at that here. So if I'm finding the critical numbers for each of these, just critical numbers. Critical numbers are where the derivative is 0 or undefined. So if I have a problem like number 4, I need to find the derivative. Okay? At this point, we should be experts in this. We are just going to get 9x squared minus 4x. And then I want to see where that is either 0 or undefined. Can that be undefined? Undefined is going to be things like, well, the main thing for undefined is going to be 0 in the denominator of a fraction, all right? That's the one we really need to be worried about. So there's no denominator for this. So we can't get undefined, but we could get it equal to 0. So if I have 9x squared minus 4x is equal to 0, how do I solve that? We take out an x, 9x minus 4. We're going to set both of those things equal to 0. So we will get x equals 0 will be one of our critical points. And then we'll have 9x minus 4 will also equal 0, where we would just add 4 to both sides. 9x would equal 4. We'll divide by 9. So x will equal 4 over 9. Okay, so our critical points for this would be at 0 and 4 9s. Now, 5, we would be looking for where the derivative of the function either equals 0 or undefined. I would have to find this derivative first. Now, what am I going to have to use to find that derivative? Quotient rule. It's still around. Or you could move it up to the top and use like a product with a chain if you would rather, if that's your thing. I would probably use quotient rule on this. Quotient rule's never simple, but for a quotient rule, this one's pretty simple. So we have low, x squared plus 1, times derivative of the high. What's that going to be? 4 minus high, which is 4x, times derivative of the low, 2x, all over x squared plus 1 squared. Now, you technically don't have to simplify, but it's going to make your life a lot easier if you do simplify. So, for this, I would distribute this 4, and I would multiply these two things together here. So that is going to be 4x squared plus 4 minus 8x squared over x squared plus 1 squared. And then I would combine my like terms up here. So that would give me 4 minus 4x squared over x squared plus 1 squared. Now, I want to know where this derivative is either equal to 0 or is undefined. If it is equal to 0, the top of that fraction has to be 0, and the bottom has to not be 0, right? It could be any number, 0 divided by 5, 0 divided by 15, 0 divided by a million, whatever. So the top has to be 0, and the bottom just can't be 0 at that same time. Most of the time it's not. I generally just set my top equal to 0. 4 minus 4x squared. You just want to make sure you don't get the same number for the numerator and the denominator. It doesn't happen very often. So I'm going to set this equal to 0. And then for this to be undefined, the denominator would need to be equal to 0. So I'm also going to say x squared plus 1 squared equals 0. And I'll solve both of these. That's going to give me my critical numbers. So for the first one, I would move the 4x squared over and make it positive. So 4 equals 4x squared. Then you would divide by 4. And so 1 equals x squared. And then we will need to square root both sides. What is the square root of 1? Plus or minus 1. There.
So if we get the same thing in the denominator.
Actually, I'm trying to think. I guess it would. It's going to give you 0 over 0. I don't even know what to do with that. I don't think it's going to happen. Yeah, really. I'm trying to think if I've ran into a problem where that happens, where you got the numerator is 0 and the denominator is also 0. I don't recall a problem where that happens. It could theoretically be possible, but I don't think you'll run into it. All right, for this, I would need to square root both sides to get rid of that square. That'll give me x squared plus 1 equals 0. I'll move my 1 over. I will get x squared equals negative 1. Oh, do y'all see a problem coming? Oh, negative under the square root. That's I. Can I show up on a graph? No, not a regular graph, which is what we're talking about here. So is this ever going to equal 0? Is x squared plus 1 squared ever going to equal 0? No. So you actually don't get any critical points from this. That happens sometimes. If I had thought about it before I even started, if I take a number and I square it, what kind of number do I get? Positive. It's got to be positive, right? Then if I add 1 to it, still positive, right? And definitely greater than 0, right? So positive and greater than 0. Then I'm going to square it again. Is there any chance that number is ever going to equal 0? It is not, right? It's just like, it's already positive and greater than 0 here. Like it would still be positive even before I square it another time, right? So it's never going to equal 0. So sometimes you can recognize it even before you like set it equal to 0 for that. So your critical points for this are just positive 1 and negative 1. Okay, so let's look at what we're going to use this for. Okay, extrema on a closed interval. Closed interval, meaning that you've got brackets A to B, right? Some sort of, in this case it's -2 to 1. Extrema, which means maximums or minimums, absolute maximum or minimums, can only occur at endpoints of the interval or critical numbers. Okay, so it can only happen at the endpoints. If we go back up here to our picture, it is possible that maybe it's just the endpoints, right? This has no critical numbers on this graph right here. Your derivative doesn't equal 0 ever. It might just be the endpoints that are your absolute maximum and minimum. But if it's not just the endpoints, there's got to be one of these places where your derivative is equal to 0 or is undefined, right? There, because at maximum or minimums, you have to have what's most common is a 0 slope on your tangent. It can also be undefined. So, if we have a problem like this, find the absolute extrema of f of x equals 2x to the third plus 3x squared on the interval from -2 to 1. And it is calculator inactive. If it's calculator active, you type it in, you put your restrictions, you look for the highest and the lowest points. Are they going to give us that question on the AP Calculus exam? They are not, because it's not a calculus problem, right? You could have done that in pre-calc, or maybe even before. So what we need to do here is, I already know the endpoints. I know they are -2 and 1, right? I need to find any critical numbers, right? So we're going to find critical numbers by taking the derivative. So like thankfully here, this is a pretty easy derivative to take. We're just going to get 6x squared plus 6x. We're going to set that derivative equal to 0 or undefined, but this one doesn't have a denominator, so it's not going to ever be undefined, right? So we're just going to say 6x squared plus 6x equals 0. What am I going to do to solve that? I'm going to pull out an x or a 6x, whichever way you want to do it. Doesn't really matter. If you just pull out an x, you'll have 6x plus 6, or you can pull out 6x and you'll have x plus 1. You'll get the same answers either way. Be careful not to like move the 6x over and divide off of x, because that x is actually going to be equal to 0 at some point. It will cause you to lose an answer, and you can't divide by 0. So don't divide both sides by x's. So we'll get x equals 0. And then right here we'll say 6x plus 6 equals 0. So that's 6x equals negative 6. And then we'll divide by 6 to get x equals negative 1. So these, you don't have to label them, but I'm going to right here. These are my critical numbers. And of course, we already had up here, these are my endpoints. All right, so the absolute maximums and minimums have to be at those points, right? At -2, -1, 0, or 1. Right? The endpoints are the critical numbers. If you get a critical number here that's not on your interval, you can throw it out. But 0 and -1 both fall in between. So all you have to do here is check to see what the values of these are. I will allow you to use the calculator for this part just because I don't want it to take us forever to do these problems. Now, on the actual AP exam, it may not be, like I'm just doing this so that homework doesn't take you 4 hours to do. Here, so what I need to find is f of x equals to x to the third plus 3x squared. I need to know what f of -2 is. I need to know what f of -1 is, f of 0, and f of 1. Now that happens to be like all the integers there. It's not always that. It can be at the endpoints. So like if we go look back up here, let me see. Oh gracious, what have I done? If we go look back up here, see how this one, my maximum was at where we'd have a critical number, where my derivative equals 0, but the absolute minimum actually ended up at the endpoint there. So you want to check the endpoints as well. And so if I look at what I've got for Desmos here, now if it's calculator inactive, you'd actually have to work it out. But let's pretend like we're just not going to go through that whole process because it would take forever, right? So f of -2 equals -4. F of -1 equals 1. Notice I'm plugging back into the original problem, not the derivative. The derivative gives me the slope of the tangent line, not the y-coordinate on the graph, which is what I'm looking for. F of 0 is 0, and f of 1 is 5. Okay, so which one of those is the highest? 5. So that's my absolute maximum. Which one's the lowest? -4. That's my absolute minimum, right? And I realize if this was actually calculator active, you could like graph this and look at it, right? I realize that. So the only reason I'm letting you use the calculator is just to speed you up on plugging this stuff in. If we're writing this really beautifully here at the end, we would want to make the conclusion the absolute maximum is 5, which occurs at x equals 1, and we would say the absolute minimum is -4, which occurs at x equals -2. So actually both your answers end up being the endpoints on this particular function, right? For that. Okay, let's try to do one more. This one's going to be a little trickier. Yes? Mm-hmm. Back out a little bit. Oh, no, wrong direction. There we go. One year I had my calculus class help my math 1 class get ready for the EOC because it was already after their AP exam. And my class was like they couldn't remember how to find a regular how to find a regular maximum or minimum for math 1. Like where they just type it into Desmos and click here. They're like, how are they going to do this if they don't know how to take a derivative, Miss Hyatt? But we don't get to use Desmos on this. So let's continue on here. So if I have basically the same thing right here, and I am looking for global extrema, I need to find the derivative and find critical points. And then I'm going to test those critical points and the endpoints to see what is the highest. So I've got to take the derivative here. It's a little trickier. I've got just 2. And then here I will have to do 3 times 2/3, which is like 3/1, right? 3's cancel, I get 2. X to the, I got to do 2/3 minus 1, which is 2/3 minus 3/3, which is going to give me -1/3. Alright, just the power rule there. It's just got some fractions, makes it a little more difficult to deal with. Now, before I try to find critical points, I think it will be easier for me to like send this back down to the bottom, make it a root. So I would have 2 minus 2 over the cube root of x. And you really, it's up to you whether or not you want to get common denominators here or not. I think it might be a little easier if we get common denominator. So like right now, I don't have a denominator here. So I need to multiply by the cube root of x in the bottom, which means I've also got to multiply by the cube root of x in the top. So I can write this as 2 cube root of x minus 2 all over the cube root of x. So for critical numbers, I'm going to set the numerator equal to 0 and the denominator equal to 0. So I'm going to have 2 cube root of x minus 2 equals 0. And I'm going to have the cube root of x equals 0. So I'm going to have 2 cube root of x equals 2 whenever I add that over. I'll need to divide by 2. So the cube root of x will equal 1. How do I get rid of a cube root? Cube. So I cube both sides, which is actually still just 1 there. Over here, I would cube both sides, which just gives me 0 for that. So my candidates that I can test here are 1, 0, -1, and 3, right? So I will be finding f of -1, f of 0, f of 1, and f of 3. It really doesn't matter what order you list them in. I like to go least to the greatest for those numbers. I really probably should make you do this by hand, but we are totally out of time right now. So let's do this really quickly. We need 2x minus 3x to the 2/3, and we want f of -1, f of 0, f of 1, and f of 3. So I got -5. Oh. 0, -1, and -2.4, or -0.240. 0, -1, -0.240. Okay. I'm not going to have time to write the whole sentence. What's my absolute maximum, minimum? -5. And what is my absolute maximum? 0. Feels wrong for 0 to be a maximum, but it is in this case. So we did not quite get far enough for you to do everything that I want you to do. So let me look at these problems, and I'm going to tell you what I want you to do tonight or tomorrow, because we don't have school tomorrow. So, so our first priority is to cheer for the Elkin soccer team, or play soccer for a couple of us there, and then we can be worried about this assignment later. Yeah, tomorrow will be fine. Huh? Well, we probably better just still do our practice, but yeah. Okay. 7 through 10, I want you to do still, because it's just a graph. Those are just graphs, okay? Then 21 through 31, we are just going to do, okay, we'll just do, so do these, and do 21, 23, and 25. Okay, do those for me. 7 through 10 are just from graphs, they're not calculus.